Hi, everyone. I'm Brittany Rockwell. I'm a product manager at Google. I'm joined by Shireen Kheradpey, who's an ML infrastructure engineer at Spotify. And today we're going to talk to you about hardware interoperability using vLLM. So first, I'll go over a very quick overview of vLLM for those of you who don't know what it is. Then we'll cover vLLM at Spotify in their production workloads. And then I'll cover vLLM TPU and what was launched last week. Then we'll go over evaluating TPUs at Spotify and how they're using both GPUs and TPUs in their production workloads. And then I want to talk about what's next. What are we focusing on for the TPU backend for vLLM? So first off, vLLM's primary goal, it's an open source inference engine, and their primary goal is really to build the fastest and easiest to use open source large language model inference and serving engine. It's really created a community flywheel because it does those things very, very well. So it's very easy to use and it's very performant. And so for that reason, model creators or foundation model builders, sorry, there's a bit of an echo, or at least I can hear it. For foundation model builders, it really becomes an important distribution channel where on day 0, you can access a model on launch with great performance right out of the box with a few lines of code. And so important distribution channel, but also it provides hardware interoperability. And so you have a diverse set of hardware backends that are also available in vLLM. So you retain the same user interface, but you can access or leverage different hardware. So TPUs, GPUs, CPUs, and many other AI accelerators. And so for this reason, the contribution trajectory of vLLM has just exploded over the last 6 months. And so this exponential growth from academics, industry, and hobbyists have really led to the amazing success of vLLM. And so I'll pass it to Shireen, who will talk about how Spotify uses vLLM in production.
Hey there, I'm Shireen Kheradpey, and I'm a machine learning infrastructure engineer at Spotify working on our machine learning platform team. And I'll be giving you a peek into how vLLM powers AI applications at Spotify. First, a little bit about what it means to be on a platform team. At Spotify, platform teams maintain the infrastructure that powers the entire ML lifecycle. And lately, we've been evolving that foundation to support AI infrastructure. So the platform spans data, training, evals, deployment, but this talk specifically focuses on the serving and inference portion of the model lifecycle. And as you've probably picked up by now, our inference stack is primarily built on vLLM, which we chose to adopt about 1.5 years ago for reasons that Brittany mentioned. And since then, we've shipped a bunch of cool AI features to users. Next, I'm going to demo a range of vLLM-based apps that we've launched, and these application launches were picked specifically because they span different input-output shapes, different optimizations and tuning strategies so that you can see how varied workloads behave differently across different hardware types. First is our entity mapping use case. So the problem here is that artist and creator moments happen outside of music. Artists can appear in podcasts and audiobooks and interviews, and we want to surface these moments to fans. And a recent example of this that happened was that Taylor Swift appeared on Travis Kelce's New Heights podcast, where she announced her latest album. And this caused many Swifties to be upset when this moment and this podcast wasn't surfaced to their feed. So to solve for this, we use LLMs to understand our content better and more proactively be able to track where different artists and creators appear across different mediums. And when feature teams say we need to understand our content better, as infrastructure teams, we hear that as we need to scale a workload across our entire catalog and also run this to keep up with daily ingestions. Next is our AI playlist creation feature. And what this is that people don't think in keywords. They don't think in 2010s or indie pop, which has largely been how users have scrolled through playlists in an attempt to capture what they're in the mood to listen to. And our AI playlist creation feature gives users the ability to describe what vibe they're looking for in free-form language, and we translate that into a playlist on demand. We can take a look at that feature here.
Desert house music for driving through Joshua Tree. I knew AI Playlist absolutely nailed it when it recommended Desert Night by Rufus Du Sol and my new Desert House Vibes playlist.
Give me chilled electronic music to manifest my dream life in the Caribbean, and boom, I got my Caribbean Dreams playlist.
So what that looks like under the hood, a user comes in and types a freeform prompt, and we use an LLM to translate that freeform text into a form that our downstream recommender tools can understand. So here we leverage features of vLLM, like structured JSON outputs, to make sure we maintain that contract when we translate from a user's input to what our recommendation tools can understand. Next feature, one that's many people's favorites, is our AI DJ interaction feature. So the concept of this is that every user gets their own personal radio host that will listen to only you, take your requests, and talk you through the music as you go. So we can take a look at that feature in action here.
It's my birthday this weekend. Can you play me some music for going out with my friends?
Music for a birthday bash with your friends. Let's do this. All right, we're kicking it off with Pitbull. Get ready for a birthday party playlist that's going to keep the energy high.
So what you heard there was our very own DJ X providing some natural language commentary on both acknowledging the user's requests, but also introducing upcoming tracks. But we only have one DJ X at Spotify and hundreds of millions of users. So to provide every user with their own personal DJ, we have to scale this workload across GPUs in multiple regions over the world. And we also leverage features like a vLLM like prefix caching. So this has a highly instructional system prompt, so we can get performance gains by using prefix caching with vLLM. We leverage tool calling to do web searches to provide extra context on top of a user's query before translating that into, again, that structured output that we use to pass to our downstream recommendation tools. The last feature that I'm covering here is safety, which appears everywhere. Let me just play this. So out of the box, safety guardrails don't necessarily apply when you're talking about music. And our solution to this is fine-tuning and prompting an LLM model for Spotify-specific policies to judge more contextual to music culture. So the technical challenges speak for themselves here. Safety is everywhere, all the time, and preferably undetectable to the user, which means that every search, every AI playlist creation, every DJ interaction has to happen in less than 50 milliseconds of latency. And in infrastructure translation, that means really optimizing vLLM using fields like max number of sequences, max number of batch tokens to really optimize for latency to be under our latency requirements for this feature. So you've seen a bunch of cool AI features that we've launched, but of course, we're never done. Now that we've launched, feature teams want things faster and to hit more aggressive latency targets. They want to deploy to more regions across the globe. They want these workloads to be cheaper, and to attain high quality, they need to continuously launch more and more A/B tests. And every one of those asks consume more accelerators or require better utilization of the accelerators we also have. And the net effect of this is that we create intense pressure on a limited GPU pool. And we have levers on GPUs that we can pull. We could reserve more capacity, add more node pools, tune the utilization to really maximize on the hardware we have. But that still leaves us vulnerable to capacity crunches and an increasing AI bill, which is what motivated our search for hardware optionality with TPUs. And with that, I'll give it back to Brittany.
Thanks, Shireen. Okay, I'll just dive in. Okay, so vLLM TPU, the first time it launched really was in April, but there was a prototype that preceded that in February that was in place. And so we worked really, really hard between February and April to land like the first implementation of TPU in vLLM. And so shortly after that, we were like, okay, we have to redesign this and take a little bit more time. And we wanted to re-architect it so that it was really, really performant and flexible for our end users. But there are a lot of things that we didn't want to change with this implementation. The first thing is that user-level APIs, we wanted to continue to support them all. Interfaces, we wanted to retain those as well. We wanted to retain the ability to run the upstream vLLM model natively on TPUs without making any code changes. And we also wanted to retain the hardware-agnostic telemetry so that it made it really easy for users to essentially move their vLLM workloads across different hardware backends without being too concerned about load balancing or whatnot. And then the base scheduler, we wanted to keep that because it was a really critical part of the first implementation. And yeah, but other than that, we really changed almost everything else. So the XLA is the TPU compiler. We completely changed the XLA lowering path in vLLM for TPU. We rewrote the runner, the worker. We improved the kernels dramatically. And then we also adopted a hardware plugin design. So a few highlights. Obviously, this isn't the full suite, but I want to highlight 3 things. So the first one being that JAX is now natively supported in vLLM on TPU. But also, we retained PyTorch as well. We really wanted to retain PyTorch support. And so now users can use both under a unified code path. The second is the ragged page detention kernel, v3, that's written in Palace. So Palace is the kernel language for TPUs. And the creator of the ragged page detention kernel is actually watching this right now, but he has a poster session later today that I invite you all to join at 6 p.m. If you want more details. And then we also adopted single program multi-data as the programming model for TPU as a default. And so this essentially creates one massive device and then shards the model across multiple devices under the hood very easily using the XLA compiler. And so what this produced was this 2 to 5x improvement in raw performance between February, which was our prototype, to today, which is now available as of last week. So we're pretty excited about that. So how are we thinking about this? So the hardware interoperability or the design or system design of vLLM, if we break up the executor, every hardware backend will rewrite their worker for the most part and their runner. Maybe not all hardware backends, but most will rewrite the worker and the model runner. And then the model code is shared. So the model definition in PyTorch lives in vLLM. But then we can also now support JAX models as well on TPU. And then if you're running on TPU, the XLA compiler is in the lower part of the stack. That's and also our Palace kernels as well. So that's the RPA v3, which is what you see. So the reason it was really important to use something called, so this PyTorch JAX interoperability was introduced so that we could support JAX and PyTorch at the same time. We rewrote these particular sections to unify these code paths so that we could focus primarily on the lower parts of the stack. So if you work in inference, you know that a lot of your engineering time is actually spent on the compiler and kernels. And we wanted to reduce the amount of time, accelerate basically development on the upper levels of the stack and spend the most time where it mattered the most for performance and flexibility. And so that was our design choice. I won't go into TorchX too much, but luckily the creator of TorchX is also here and has a session. Actually, he's just walked in. Hey, Han. You can go talk to him. He will go over TorchX at length about this really incredible interoperability between PyTorch and JAX at 6 p.m. And then ragged page detention, this really unlocked for us. There were a couple of really important design decisions that were made, particularly fusing the KV cache management operation, so the scatter op, with the ragged page detention kernel. And this completely eliminated the scatter latency in the RPA kernel, which dramatically improved performance. It also improved deployment flexibility because there are 3 different subkernels now. One is prefill only, decode only, and then mixed. This allows us to also support deployment patterns like disaggregated serving out of the box. And then, of course, there's no compromises. Just because we made it more flexible does not mean we made it less performant. And so please go talk to Jevin Zhang and Yorong Mu for their session at 6 p.m. I'll now pass it to Shireen, who will go over how Spotify evaluated TPUs in their production workloads.
Yeah, so now I'll be showing you what TPU performance looks like for real-life AI applications. So going back to those applications that I demoed previously. But first, a quick callback to what I mentioned before. We are in a hardware pinch, so the demand for GPUs continuously climbs and capacity is getting very competitive. And in parallel, as Brittany mentioned, TPUs have matured and the vLLM TPU backend allows us to run our AI workloads on TPUs with minimum configuration changes. So given that GPU squeeze and TPU readiness, this motivated us to benchmark TPUs as an additional accelerator option. So not to replace GPUs, but to add to that optionality and relieve some of that resource pressure. So we had two benchmarking setups, batch and real time. And for the batch benchmarking setup, we optimized for throughput workloads. And this includes using Ray as to orchestrate work distribution and using vLLM as a library to perform optimized inference. And we track the outcome of job duration, which allows us to then calculate the average throughput as well as cost per millions of tokens. The results that we saw, this is for the entity mapping use case. So mapping when your favorite artist might appear across different mediums. And this is a relatively prefill heavy use case. The data shape is around an average of 1,500 tokens input and a max of 100 output tokens. So we held this data set constant over H100s as well as TPUs and measured the job duration for each. And you can see our results. On the left-hand side is the throughput, and the leftmost column is H100s, and the rightmost column in each graph is the results for Trillium TPUs. And just as extra insight, I left a middle bar, which was actually our initial TPU benchmark that we did months ago. Whereas the rightmost column is the final TPU benchmark, including all of the new launches that Brittany covered. So this includes the launch that happened last week. And you can really see the improvement benefit just within those changes. So looking at the results, we found that the Trillium TPUs yielded about 14K tokens per second as an average throughput over our data set. And now with this new TPU backend, we're saturating the TPU, and that remaining speed gap between TPUs and H100s is hardware driven. So H100s have a higher HBM bandwidth capacity when compared to Trillium, and that's what yields the difference in performance between the two. Even though H100s win on raw speed and raw throughput, Trillium actually wins on overall cost performance. So we calculated Trillium to yield around 48 cents per million tokens. Now onto our real-time latency setup. So here we use vLLM API server running on GPUs and TPUs. And our goal here is to find the maximum sustainable queries per second while meeting the SLOs for each of these applications. So back to the AI playlisting creation application. This is actually our most decode heavy of the demoed workloads since we have a maximum output token size of 1,000 tokens. And this workload is most likely memory bandwidth bound, which is common for decode workloads for LM inference. And during decode, we are generating tokens one by one and repeatedly reading from KV cache. And all of these reads create a lower arithmetic intensity, so performance is then capped by your HBM bandwidth rather than your raw flops. And this is reflected in the shape of the graph which is our latency CDS comparing different hardware types. You can see the knee happens more quickly for TPUs, and this is because we're saturating the TPUs more quickly than GPU hardware types, where we have that higher HBM bandwidth. But despite that, we calculated out we'd need around 2x more TPUs to serve the same workload, and this yielded a 62% cost savings for Spotify. For our AI DJ interaction model, this is actually a use case that we chose not to pursue at the time when we were benchmarking a few months ago because of a mismatch in quantization availability. So the quantization methods that Spotify used for our model weren't available with TPUs at the time, but they are now supported with the new TPU release, or the new TPU backend vLLM release. The last use case, safety. Here, TPUs win on raw performance and on cost efficiency. So safety is our proportionally heaviest prefill workload, since we take an entire system and user prompt and return just 1 to 2 tokens, since we're using this LM as a classifier model to really classify whether content is violative or not. And in LM serving, the prefill phase is when you're processing a long input prompt, is where these large matrix multiplications happen and attention over many tokens happen. So this creates a high arithmetic intensity, which is where we saw Trillium excel. So we see that in the fact that the Trillium TPUs were actually able to sustain 1,000 queries per second, which is about 4x the queries per second that we saw with our existing GPU workload, while holding to our aggressive P99 latency of under 50 milliseconds. So displaying these workloads side by side gives us insight into when we could pursue using Trillium TPUs in vLLM. And again, emphasizing we're not trying to move every workload to TPUs, but our goal here is optionality and providing guidance on when TPUs give better performance per dollar. So it would make sense for us to consider moving that workload to them. So on this chart, we found that all workloads did perform more cost effectively on Trillium, but to different degrees. So the best cost efficiency correlated with those prefill heavy use cases like safety that has a long input and a short output, but the gains were smaller for those decode heavier workloads like the AI playlisting creation. So a rule of thumb, if a workload has a long input, short output, then Trillium tends to exceed. But as the decode length grows or your output length grows, H100s can potentially catch up and potentially even win due to that HBM bandwidth limitation of TPUs, or of Trillium. So what's next? Well, some things that we're looking forward to next are, we have an eye on how TPUs improve on these decode-heavy workloads, and we've also been seeing an increase in multimodal interest and multimodal inference workflows. So we're looking forward to trying out some multimodal workloads on TPUs. And with that, I'll give it back to Brittany.
Thanks, Shireen. Okay, what's next? Don't have too much time. Okay, so we're launching Ironwood between now and the end of the year. We're starting with private preview next week, and then public preview in November, and then we're launching in GA in November, December. Ironwood is very different from Trillium, and so Shireen went over Trillium. The uniqueness of Trillium. Trillium is, very T-flops heavy, right? But HBM bandwidth limited. Ironwood is kind of not the reverse, relatively speaking. And so 4.5 times the HBM memory bandwidth is available on a single Ironwood chip. It is 6 times more HBM capacity, so you can serve much larger models on a single host, and then 2.5 times more T-flops. So notice how the relative numbers there are slightly different. The scale out of Ironwood over ICI, which is our fast interconnect for TPUs, can scale up to 9,000 chips, which is really like a massive pod, probably not needed for inference, but just in case we have some training folks in the room. So if we think of Ironwood, so again, this is what we're working on next. So Trillium, small models, prefill heavy, latency sensitive. If you're very latency sensitive, Trillium might not be the chip for you. So our focus now is really on Ironwood. So what Ironwood means for us is we can now start to scale XL MOE models on Ironwood. So that's our focus. terms of the data distribution, think reasoning models, so very decode heavy, large scale implementations or serving, inference deployments, and then ultra low latency because of that extra memory bandwidth. So another focus of ours is on LMD. So there's probably some LMD folks in the room. So Kubernetes, orchestration based, or you can think of LMD as an opinionated way of stacking a bunch of composable parts in open source to make up a really high performant inference stack. And so integration into LMD is really important. vLLM is the backend inference engine for LMD. And so we're excited about this integration work. Another big focus of ours is distributed RL integration. And so with our friends from Tunix, which is the JAX-based RL framework, in addition to SkyRL, which is the PyTorch RL framework that we're integrating with. If you're really interested in what we're doing, please join us on GitHub. You can check out the vLLM project at the main repo, but also do check out TPU Inference that just launched last week. And again, I welcome everybody to go to the Google hub downstairs, or I don't know what to call it, because there's also a new project with running PyTorch on TPUs that everybody should learn about. So thanks so much.